Ivar Thorson, and today I'll be talking about how sunflowers lead to another musical scale. And what is this about? And I chose this title a few months ago, not really knowing what I was going to talk about, and then had to put the whole presentation together yesterday, pretty much. And I wanted to talk about music, because I've been interested in music. And I also was looking for somebody who might like math and talking about math, and I figured a bunch of programmers would be a good group for that. And when you talk about music, you have to go a little bit into history. And music has some psychophysical aspects, like how do we perceive different sounds and things like that. My wife's a neuroscientist, and I hear her about all the time. And then kind of there's some kooky numerology associated with math and music and all those other things. And hopefully I won't get too kooky this evening. But I did want to talk about what patterns occur in music. How many people here were in band or play an instrument or do something like that? Okay, good group of people. Now, when I was in band, I could never figure out what notes to hit. And so I always had about a 50% chance of hitting the exact wrong notes. And it's always left this impression on me where I wished I knew what the patterns were that I was supposed to follow to play music. Another thing I've been kind of thinking about is, why does everybody like music? I mean, has anybody met someone who doesn't like any kind of music, like totally amusical? I've only met one guy in my life. So, I guess more broadly, like, if we like something about music that's sort of more universal, like what would it be like if there were music in the future? You know, how different is music today from when it was 1,000 years ago, and what will it be like 500, 1,000 years from now? Or if we met aliens, would they like music? So I'd say the main themes of tonight, even though I could talk about this for a while, is consonants, what it is, dissonance, and then hopefully talk about sunflowers, the sort of experiment I'm working on. So the first thing is we'll talk about a vibrating string. If I take a guitar and I pluck it, I can get it to, and I don't know if this will work. Oh, great. We can get it to vibrate at the fundamental frequency of that string. It'll vibrate in this way. But we could also get it to vibrate by putting your finger. Is that a little too loud? A little too loud. I'll adjust it up here if you want. If you can play the harmonics of a guitar by placing your finger gently on it, for example, halfway, dividing it in half, or in a third, or in 2/3, and plucking it near the bridge, you can get it to produce different sounds. And if the bottom string was vibrating at 110 hertz, the first harmonic above that would be 220 hertz, and then the third string would be 330 hertz, and so on. And every time you pluck a guitar string, it's vibrating in all of these ways simultaneously. And we call that the timbre of a musical instrument. The relative strengths of these higher harmonics influence how we perceive that musical instrument. And if I play the first 5 harmonics, this may sound familiar to some people who've watched 2001: A Space Odyssey. Does anyone know what the next note is going to be? Dun, 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 dun. But no, actually the next note is a G, and it sounds like that. He chose the ratio between these two harmonics to be which is a minor note. So down here at the bottom, I've got range of human hearing, roughly 20 hertz to 20,000 hertz, and you can see, because this is a linear scale, almost all the notes were there at the very bottom. So Pythagoras discovered a couple thousand years ago that simple ratios of frequencies are consonant. And if I play a 2-to-1 ratio, I've now added those harmonics in the blue and the red. I'll play this a couple times. Blue and red, and you can see that the red and the blue overlap every other note, or every other harmonic. And so that reinforcement of the harmonics is somehow pleasing to our ear. If I play a 3-to-2 ratio, we call that the fifth in music. And why do we call something with a 3-to-2 ratio a fifth? Doesn't make a lot of sense, or we call it a CG. Same thing for fourth, third octave. Really, we should call this like dyad or triad or two. We should have probably different terminology for it in music. So a musical third playing a C and an E produces a 5-to-4 ratio, and so on. Whereas if you have something that's a complicated ratio, like 18-to-17, that sounds unpleasant to us. So somewhere between very simple ratios and very complicated ratios, we find music. And you use the more complicated ratios to to produce dissonance, and then you resolve them with consonants. You can just play lots of notes here, and that's kind of fun. This is my first time programming Clojure script, which is then compiles to JavaScript, and right now this is being web served from the phone over there from my dev box, and this is just like very strange that this is working at all for me. Pythagoras, we're going to talk about the old tuning that was developed by Pythagoras, and it was based on these really simple ratios. Legend has it he was hearing a blacksmith hit two hammers together, and he thought, oh, those sound really nice together. I wonder why that is. And he went and looked at it, and he found that the weights of the hammers had a 3-to-2 ratio. And he played around with it a bit more, and he discovered that lengths of strings and bells and things with mass could be related by simple numbers. So he developed the Pythagorean tunings, where relative to the lowest frequency, if you divide relative to the lowest frequency, the 8 notes in the scale, which is where octave comes from, have these ratios. And if I play it, sounds pretty familiar. A major scale, we'd say nowadays. And between each of these notes, there's an interval that is produced. So if this were 400 hertz, this would be 400 times 9/8 hertz, and the ratio between them would be 9/8. And if you were to have then multiply 400 hertz by 81/64, the ratio between that note and this note would be that times that, which is once again back to these simple ratios over here. So it has a lot of really nice qualities to it. Oops, we didn't mean to do that. But the problem is these intervals between all of these notes are irregularly spaced. And so if you want to play in a different key, it sounds a little different. It doesn't quite sound like a major scale anymore. And these are the classic modes in music. Oops, didn't mean to do that. Oops, okay, so here we go. So now we're going to get into what like a log scale is and what modern music sounds like. So modern music, I'm displaying now all of the harmonics on a linear scale at the top up here and a log scale down here. And you can see that if I play these low notes on the linear scale, all of those harmonics are really compressed together. And apologize for this, I'm going to play a high note now. They're much more spread out because the fundamental frequency is higher in this case. So on the log scale, however, they're all about the same distance apart, no matter where you play, because this process of multiplying things together actually becomes sort of evenly spaced. So the linear view is useful for seeing ratios and consonants, because it's easy to see when something lines up or doesn't line up. And the log space more corresponds to our perceptual understanding of music. We can perceive small variations of 1%, maybe 0.5% if you're good, in the pitch of something. But so we'd be able to maybe perceive the difference between 100 hertz and 101 hertz, but we wouldn't be able to perceive the difference between 10,000 and 10,001 hertz because the relative difference is smaller. So I just made this little widget to play with different things, and you can play with a Pythagorean scale and so on. Or we could do the entire piano very quickly. Whoa. And if we play with the various chords, there's a 2-to-1 ratio, a 3-to-2 ratio. In fact, pretty much all of these simple ratios sound fairly familiar and pleasant to us. So, I don't know about you, but when I play the Pythagorean scale and the white notes on a piano, they sound very similar to me, but in fact they are different because they're based on a different scale. And modern equitemper tuning is based on this idea of 2 to the 1/12th power, about a 6% difference in the relative pitch of every note in the scale. And the advantage of that is then all of the intervals between each half step in a I apologize if I'm losing people in the audience, but this is you have to talk a little bit about music theory before you can talk about the different strategies, I guess. The modern equitemper tuning, all of the ratios are the same, so it's very easy to transpose from one scale to the other. But you lose the classical advantages of consonant things, of having these harmonies and these harmonics line up very perfectly. So I went and computed how inaccurate the modern scale is. Even though we've gained this ability to transpose things, we have lost the perfection of these really simple ratios. So for a fifth, the actual note, when you take 2 to the 7 over 12, because it'd be the 1, 2, 3, 4, 5, 6, 7, and you are playing the C and the G together, that is actually very close, within about 0.1% of the true number. However, for the sixth, we're actually quite inaccurate. And if I play both of these at the same time, you might hear something that sounds a little unusual. And you can kind of hear some beating and some warbling, and it'll depend on the music, or sorry, the instruments that are playing the music, on how much of that warbling and unusual sound you'll get. So when you tune a guitar, for example, you might end up having a better tuning for one particular key, but not another. So to review, all sounds have many harmonics. The relative volumes of each of the harmonics determines the timbre, or the type of instrument that you hear. The simple ratios sound consonant, and that's probably because the harmonics line up. The modern musical system is harmonically imperfect, but hugely convenient for transposition, and we can't really hear small errors. So what if people in the future could hear these errors, or what if we met aliens? What kind of music would they like? Would they think we're just doing really bad approximate music? Or can we visualize this consonant that is just below our hearing, but maybe in the future we'll be interested in? So I made this crazy spiral plot thing. And basically it's the same line of the hearing that it represents that same line of what sounds we can hear. But instead of being, let me pick a better one here. Let's pick a fifth. Instead of showing the amplitude as a colored line, it now shows it as a colored dot. And so when I play unison, the blue and the red colored dots line up on the same line, and each turn represents 440 hertz in this particular case, but you can tune that to make the different shapes if you want. A perfect 3:2 ratio would line everything up on a line, and in our scale it's very slightly off. A fourth would form a triangle, but in the modern musical scale it's slightly off. It should be something like that. A sixth is quite off. A minor sixth is also quite, or sorry, a major and a minor sixth are both quite off. And if you were playing a major chord, you can also tell that they don't line up on these sort of radial lines of the square, and that would be a more harmonically consonant sound. Same for a minor, or you play both at the same time. And I'll try to put this up online so people can play with it and I guess have more fun with it. And so my contribution is to wonder, what's the most dissonant thing possible? And if you're talking about ratios, you want to have something that's really irrational, that the harmonics are never going to line up. I had grand visions of trying to develop a new type of music, but I seem to only have developed the worst kind of music possible. And I'm not going to get into it, but you can take, if those of you who know about repeated fractions are a mathematical concept that allow you to express decimal places in any base. You could be base 2, base 10, it's all the same. And you can also use these numbers to make approximations. Like if you were to take 21, which would be 3 times 7, divided by 3, that's a pretty bad approximation to pi. But as you continue to work out these numbers, you end up with more complicated ratios that can approximate pi to better and better precision. And the larger this number is, the better the approximation, the more decimal places of accuracy you get. So the worst possible, the slowest converging irrational number is phi, 1.618, which is nature's number. And the worst possible number in the modern tuning system is the tritone or the wolf tone, which is basically the square root of 2. And it corresponds to, just go back for a second, it corresponds to like a C and an F sharp. That would be the most dissonant number, one possible. So I tried some of these just to see how bad they sound. Here's pi, doesn't sound great, but that's also like a little bit too high, so I did pi over 2. Still not a really pleasant number. Square root of 2, also not great. And here's I'm positing this, don't have any proof, that that's the worst note you can possibly play. And I think I learned that back in school. So then, I guess my final contribution was I tried to make a tuning system based on this worst possible note. And my idea for doing this was going to be clear in a second here. If I take and go 0.618 around in the first rotation and then continue doing this over and over and over and over and over, this is tiling this frequency space in an irregular way so that none of the notes will be consonant to each other. But maybe this will actually sound good to us. I haven't really figured out how to do this yet or how to like organize it, but some of these will be close to ratios we do find pleasant, and others will be really not close. And if you look at this, and you look at sort of the spirals that are formed by this, you can kind of see a spiral going one way and kind of a spiral going the other way. That is a sunflower, which is where I'm going to end my talk. And I hope you enjoyed learning a little music theory, and talk to me if you're interested in this. Bye-bye.